When a massive star dies, it can leave behind a neutron star. And when they first happen, they're rapidly spinning and can be letting out radio flashes. We call these pulsars. But very rarely, you get these weird objects known as magnetars with incredibly intense magnetic fields. Classically, we say how they could tear you apart at an atomic level with these magnetic fields. And astronomers aren't entirely sure what is the mechanism that causes them to form. One really interesting idea is that you get magnetars out of kilonovae, where you have two smaller, less massive neutron stars collide with one another, and they don't produce a black hole. Instead, they produce an extremely massive, rapidly rotating neutron star that is surrounded by magnetic fields and all of the debris left over from the kilonova explosion, and that can help power a magnetic field that is so intense and so strong. And so to find objects like this, you want to scan the afterglow, the wreckage of recent kilonova events to see if there is a magnetar there lurking inside. And my guest today has done exactly that. Her name is Dr. Genevieve Schroeder. She's a postdoctoral researcher at Cornell University, and she works with the Zwicky Transient Facility. Dr. Schroeder and her team did follow-on observations for a kilonova that happened a little over 10 years ago, looking for, in the afterglow, is there a magnetar at the heart of this expanding cloud of debris? And could this be a possible explanation for how you get magnetars? What did she find? Well, you're going to have to watch the interview. But if you're fascinated with the idea of magnetars, supernova, kilonova, all of these extreme events, I think you're really going to enjoy this conversation with Dr. Genevieve Schroeder. Dr. Schroeder, tell me about GRB, I have to look at my reference, 211211A.
Yeah, so GRB 211211A is how I typically say it.
Yep, that makes sense. It's the year and the...
Yeah, the year, the month, and then the day that we discovered it. And then the A says that it was the first one we discovered of that day. It was a really exciting GRB because it, first of all, was very close by. Typically, we detect these gamma ray bursts quite far away, which can make it difficult for us to follow them up, or if we are following them up, we're not able to place a strong of constraints on how luminous they might be. But because this one was so nearby, we were able to really dig deep into how bright this thing was. So that was one of the reasons it was interesting. But the other really interesting thing about this is so gamma ray bursts as a whole typically come from these two different progenitor channels, either two neutron stars merging or one massive star collapsing and dying. And usually we can use the gamma ray duration to determine which of those progenitors it came from. So if we see the gamma rays for less than 2 seconds, then we assume that it came from a neutron star merger. Whereas if we see the gamma rays for longer than 2 seconds, we assume it came from the core collapse of a massive star. But GRB 211211A was really interesting because we saw the gamma rays for much longer than 2 seconds, but it didn't look like it actually came from the core collapse of a massive star. So these core collapse GRBs, they typically have a very specific type of supernova associated with them. We didn't see that at all for this event. And then also we saw this very red transient. So red as in it was brighter at infrared wavelengths than optical wavelengths. Much earlier on than we would expect a supernova. And it looked so similar to what we saw following a known neutron star merger, which is GW 170817. So
right. The classic kilonova.
Yes, the classic kilonova. Yeah. So this GRB is so cool and interesting because we think, even though it has these really long gamma rays, we still think it came from a neutron star merger based off of the fact that it looks like a classic kilonova. And one of the explanations for why are we seeing these gamma rays for such a long time is that maybe when the neutron stars merged together, they produced an even bigger neutron star, which would be a magnetar. And that magnetar could produce this like extended emission of gamma rays that you might not always see if the two neutron stars merged and created a black hole instead.
Right. And I guess 2112 was too early for LIGO to be able to have made an observation to confirm that it was a kilonova.
It was during one of the time periods where LIGO was offline, unfortunately, but
Right.
it is also just far enough away that we're not sure what constraints LIGO would have been able to place. So currently, the observing run that just ended for LIGO could see out to about 200 megaparsecs, and this event was at 350 megaparsecs.
Right. Right. Yeah. So it would have been a tricky find even for LIGO if it was in fully operational in its modern state.
Yeah.
Yeah.
But it would have been really great to at least have it on so some limits could have been placed, whereas it was completely offline. So we have no idea if it would have seen anything.
Right. But because of the Kilonova event, as you mentioned, we saw this beautiful connection between what we knew was the merger of these neutron stars with the afterglow that was seen across the electromagnetic spectrum. And so you saw an object, when you look at it, that is very similar in the kinds of afterglow there.
Yes, exactly. So also with like the core collapse GRBs, typically they are much more luminous than the neutron star merger GRBs in terms of their afterglow. So even on that realm, we think that like if this was somehow from a core collapse GRB, it would be way under luminous, and that would be very surprising.
Right. And, I remember with the Kilonova, I guess now, like hopefully a kilonova, but the kilonova, that a lot of people were speculating on what would be the remnant left behind. Would you get, as you say, possibly a magnetar? Would you get a black hole? Have they identified a remnant for that one?
No, so they have been searching for any type of like later emission based off of, because again, this was the one that we are talking about, it was detected by LIGO, so we actually have a constraint on the actual masses of the neutron stars that merged. And based on those masses, we expect it should have been a hypermassive neutron star, which is something that only exists for like milliseconds before it collapses.
Oh, wow.
Yeah. So that's the like running theory right now, but unfortunately with that kind of neutron star, it doesn't really live long enough to really imprint on anything around it. So it's much harder to make constraints on what it was.
But you would have, like, theoretically, the two neutron stars would have come together. You would have ended up with a thing that is a neutron star, but it's too much of a neutron star, too much mass, and so it would have collapsed into a black hole at that point.
Yes, exactly. So
or
it was
exploded again, but you would see that. So it would have been, there was no other explosion. So
yeah, so it would have just been a direct collapse. But yes, as you were saying, the masses would have been, the mass of this like potential neutron star would have been just a little bit too high that as it started to spin down, it's not like gravitationally supportive against becoming a black hole.
Right. But if you had two neutron stars with less mass, you're theorizing that you could get this merger and it wouldn't cause this immediate collapse, and you would be left with a super heavy neutron star, which I know some very massive neutron stars have been found. That would be exciting on its own. Why is this connected to the possibility of a magnetar?
Yeah, so we just sort of assume that this, if there is this like neutron star that can exist after a merger, individual neutron stars already have really high magnetic fields. So the assumption is that when they merge, that those magnetic fields can sort of compound on top of each other, and that would push it into like the magnetar territory.
Right. Yeah. And I mean, these magnetars have magnetic fields that are just ridiculously stronger than the garden variety neutron stars. And I know that when you get your neutron star, that's how you get pulsars, is fresh neutron stars, fresh supernovae. but magnetars are rare and ludicrous. So is there some kind of, what are the possible events that have been theorized that could give you an object that's that extreme?
Yeah. So the most robust way that we believe we get magnetars are from individual stars collapsing through a core collapse supernova. And I believe right now the main theory for that is a special type of supernova known as a superluminous supernova, where this extra luminosity is due to the fact that a magnetar was formed and is sort of pumping extra energy into the supernova. And then other potential signposts of magnetars, at least, are things like fast radio bursts, which it's a very large prevailing theory that at least some fast radio bursts come from magnetars. But again, that likely would have been produced by some type of supernova earlier in time. So I think there's also things like accretion-induced collapse of white dwarfs could potentially make a magnetar. Don't quote me on that, but I think that's one avenue. But yeah, typically either one individual star or maybe, again, the merger of two things could potentially make these.
Yeah, and I know as well that there's potential interactions with a binary companion. Something has to feed its spin and set up this magnetic environment around it that it can interact with to produce such powerful magnetic fields. So it's not normal, whatever it is.
Yeah, it's definitely a smaller percentage of the neutron stars out there are these extreme objects.
Right. And so far, astronomers have not seen that smoking gun yet. They haven't seen there was a precursor, there was an explosion, now there's definitely a magnetar.
Yeah, I believe we've seen things within our own galaxy that we're pretty confident are magnetars, but again, we didn't see it become born.
Right.
We've just seen certain emission that makes it very difficult for it to be anything else.
Right. And so this is an example where we saw the supernova, potentially a precursor event. You were hoping to find a magnetar in the wreckage. And so what tools did you use to do the search?
Yeah, so to sort of set up the idea behind it all, we have, again, these two neutron stars, as they're merging, they are tidally stripping each other, and they're producing this massive ejecta that turns into the kilonova that we observe. And so if we have this massive neutron star remnant that is a magnetar, and it's spinning down, it has to deposit all of that rotational energy into that kilonova ejecta. And so that's going to boost this kilonova ejecta. And so now the kilonova ejecta is moving faster than it was before. It has more energy, and it's interacting with all the surrounding material. And that's going to energize the electrons and produce synchrotron emission. So this synchrotron emission, which is similar to what we see in the afterglow, except it's going to be peaking at different wavelengths and at different timescales. So for this boosted kilonova signal, we are expecting it to peak at radio wavelengths, and we expect it to peak years after the merger. So if it's peaking at radio wavelengths, then we can use radio telescopes to search for this, and we just do targeted observations of merger GRBs a year to several years after the fact. The radio telescope I personally use is the Very Large Array, but I've also used Meerkat to do these studies because those are the two most sensitive at the frequencies that we require.
Right. Yeah. I've been to the Very Large Array. I haven't been to Meerkat, but obviously, Meerkat is the precursor for the upcoming Square Kilometer Array, which has just got to feel amazing to sort of see this field coming together, pardon the pun.
Yeah.
So and it's interesting that there's that delay that it often with astronomy, especially with supernova, you're wanting to make those observations immediately, the closer seconds count in this case. But what you're looking at, the signals start to show up later on as it's interacting with its environment.
Yes.
And is there sort of like a window where you'd be like, okay, we should start seeing it now, and then it's too late if we get to this point?
Yeah, so it's a little bit dependent on which models you believe, but basically the rise and fall time are dependent on the mass of the kilonova ejecta itself, and also the density of the environment that this merger happened in. So the kilonova ejecta has to sweep up about an equal amount of mass within the density in order for this signal to peak. And so if a merger is happening in a denser environment, then we would expect peaks sooner, on years-ish timescales, where if they occur in a less dense environment, then it could take longer. But the problem is also the less dense environment will typically produce a less bright peak, so it's much harder to constrain that. So this event, 211211A, was really great because, again, it's nearby, so we can probe deeper in luminosity, but also it seems to have occurred in a relatively dense environment, such that we think the peak should be early and it should be bright.
Right. And so what did you find?
Nothing.
Right. The famous null result.
Yeah, so this was an interesting study to do. So we've done a lot of studies in the past looking at short GRBs from neutron star mergers, trying to find this. And so far, there haven't been any solid detections. But we were hopeful that with this event being so much closer, we would be able to detect something. So far, we have detected nothing, but at least it's consistent with every other observation of other GRBs.
Right.
But that doesn't mean
no other
that
astronomers have been lucky either.
Yeah, exactly.
Yeah.
But that doesn't mean, this was all for naught. What it does mean is we can start to place constraints on how much energy was put into that kilonova ejecta. So, basically, if the two neutron stars that merge produce a remnant that is less than the maximum mass of a neutron star, that remnant can exist forever. It will slowly spin down, and then it's just hanging out as a neutron star for the rest of the universe, basically. And we expect that something like that should be able to put up to 10 to the 53 ergs into the kilonova ejecta. However, if the neutron star remnant is a little bit above the maximum mass of a neutron star, it can exist long enough to spin down a little, put some of its energy into the kilonova ejecta, but then it's going to collapse into a black hole. So we expect that amount of energy to be between 10 to the 52 and 10 to the 53 ergs. So for this study, I was able to place constraints of about 4 times 10 to the 52 ergs, which means that we don't think the resulting neutron star lived forever. We definitely think if one was created, then it had to have collapsed into a black hole.
Wow. And I wonder though, I guess neutron stars are already the result of a very extreme star that is dying, and you have this constraint. If you have too much mass, then you get a black hole, and so that automatically constrains the mass that's going to be in the precursor of this neutron star. And if you bring two of them together, you must, do you have any thinking about what percentage of the time they probably just collapse into a black hole? And then is it most likely it's black holes, or is it most likely it's supermassive neutron stars?
Yeah. So again, we've done these studies in the past looking at other short GRBs. And so in 2020, I performed a somewhat similar study with relatively nearby short GRBs. They're still much further than this event. But based off of that, I was able to predict that around I think it was 50 to 80% of short GRBs must create a black hole, just based off the fact that we haven't detected this emission yet. And then also, we know from the Milky Way, we have a couple binary neutron stars within the Milky Way that we think should merge within a Hubble time. And if we are able to measure their masses pretty well, which we have been able to do, we see that their masses sort of peak around, like, I want to say 2.5 to 2.7 solar masses. So that's the combined mass of the two neutron stars.
Right, and sorry, and what's that sort of theoretical upper limit?
So that's a great question. Definitely below 3.
Yeah.
But a lot of people put it somewhere between like 2.2 and 2.5. So if we know that our like Milky Way binary neutron stars already kind of push above that limit, then we would not be surprised if throughout the like universe, binary neutron stars are also above the like 2.2 to 2.5 limit.
Right. I know that astronomers think that there could be an in-between step between neutron stars and black holes, like maybe some kind of quark star or strange star, some point where you feed a neutron star enough material that it collapses down one level. Do you think that this could be a way to potentially detect or place constraints on whether these objects even exist?
That's a good question. That is a little bit outside my wheelhouse on the like theoretical side, but I would be interested to see what some of the people who think about this very deeply in theory would have to say about that. Yeah,
I mean, the kind of the traditional idea for this is just that you've got a neutron star that is accreting material from some companion star, like a white dwarf gets you a nova or a type 1a supernova, and that you cross some line gently that then you can collapse down one level and end up with a thing. And so where are they, right? What would their signals give off? But this sounds like it could be a completely different avenue to get you there. And I wonder though, if there's something that happens in that transitional phase when you go from I'm going to call it a supermassive neutron star at this point, but when you get this neutron and then it shifts into that black hole, is there some special signal that you'll see? It'd be interesting as we find more of these things out there.
Yeah, I would find that very interesting. And I think there's some evidence, or people point to certain things as evidence of seeing that happen, where, you know, sometimes in these short gamma ray bursts, we see this plateau that like immediately shuts off. And some people have suggested that when we see the plateau just like shut off, maybe that's when it immediately collapses into the black hole.
We need more. Like, what do we have? Like 3 potential kilonova events detected by the gravitational wave observatories. 1 for sure, maybe 2 more. Like, it's not a lot.
Yeah. So, you know, this next era of like transient discovery with things like the Rubin Observatory's Legacy Survey of Space and Time, I think will be really interesting to try and capture more of these. And I also know like the current plan is for LIGO to turn back on for a little bit of 2026 to sort of sync up with the beginning of...
Oh, interesting. I didn't know that. Okay.
Yeah, it's on their website now. So they had officially ended like 04, and they were supposed to go into a shutoff for a couple of years until 05. But because Rubin is turning on, they, I think, wanted some type of overlap to sort of help people, you know, vet all of their pipelines trying to search for kilonova.
Yeah, that's really interesting. So getting a null result, I'm sure, kind of focuses the mind, and now you're like coming back at it and thinking about other objects out there and thinking about other observations that you would make. And so are you mulling over how you would be taking another crack at it to find the objects?
Yeah, so there's a couple different things that are like on my mind with that. So for one, even if there's like no magnetar, if this neutron star merger immediately forms a black hole, the kilonova ejecta itself does have a little bit of energy. It's like 10 to the 51 ergs, so not like 1 to 2 orders of magnitude lower than what we've been
merely
talking about. Yeah. But there is theory to support that even that amount of energy, as it like interacts with the surrounding medium, it should be able to produce its own synchrotron emission. This is known as the kilonova afterglow. And so people have been searching for that with 170817, and so far it's still like upper limits for that as well. But that was something I had tried to constrain for 211211A. And what I found is that it might be peaking around this time, like right now. So I have a VLA program that will start at the end of February, where I will observe a couple different short GRBs, mostly to search for this like magnetar boosted kilonova, but then also for 211211A to search for its kilonova afterglow. So that's one avenue. And I think also continued follow-up of short GRBs or other weird GRBs that might come from mergers. But I think another interesting thing is looking towards radio surveys rather than targeted radio observations. So the boosted kilonova signal that I was talking about, it should be like quasi-spherical. So even if we don't see a short GRB, we should still be able to detect that. And obviously, if we don't see the short GRB, we don't know where to look. So looking at radio surveys is the best way to search for it. So then
and
we
I know,
have
like Meerkat, like you've got these incredible radio surveys they've done where they almost look like photographs. Like it's amazing to see the level of detail coming out of Meerkat. And again, that's just like preparation for what it's going to be like having access to the square kilometer array. And so do you see, we've got Gaia, we've got Rubin, we've got all of these large surveys. Are we going to get to this place where there's just this kind of continual survey of all things radio in the sky to that level of resolution that you can see these, there's all the magnetars that just formed?
Yeah, I think that it's a very hopeful thing. So, we have the deep synoptic array. That's sort of our version of all of this in the radio, where it will be a all sky survey over the course of 5 years, but it will look at the same patch of sky approximately once every couple months, depending on the like exact observing strategy they determine to do. But the great thing with it will be that it's so deep. So it's going to get like way deeper than any other radio survey. Well, maybe not Meerkat, because Meerkat's incredible, but things like the VLA Sky Survey or the Rapid ASCAP Continuum Survey, which are our current state-of-the-art radio surveys that cover like large patches of sky. It will be so much deeper than that, which is so incredible. And then it will also have the cadence that kind of matches. So like the VLA Sky Survey is great, but it looks at the same patch of sky every like 2-ish years. So you might miss things that need you to like look more quickly, but instead having something that looks like every few months will get a little bit better like time resolution for some of these things.
Dr. Schroeder, what are you obsessed with right now?
Yeah, so we've already talked about some of it, but I'm really obsessed with like the new surveys coming online. I'm so excited for Rubin. I'm so excited for the DSA. I think those will really revolutionize the field, and it's going to be a very exciting time. I typically focus on the radio follow-up of all energetic transients on timescales of hours to decades. So some of the things that we are interested in right now are like fast blue optical transients, which are discovered in the optical. We think that they're some type of like massive star dying, but they could also be like a binary companion to a smaller black hole that's sort of doing a tidal disruption event.
Yeah, we just reported on this just like a day ago about one of these.
Was
it that conclusion? Yeah.
Was that for 2024 WPP?
I don't remember which specific object it was, but it was, a possible answer is a stellar mass black hole tearing apart a stellar companion, finally getting its hooks into its stellar companion, tearing it apart. Then you get this super weird, very rare event that has been seen a few times now. Yeah,
it's so cool. So like last September of 2024, we detected one, which was 2024 or AT 2024 WPP. And I helped do the VLA radio observations of that. And it was a paper that was just submitted by Daniel Hurley, who put all of the observations together. But things like that, I think, are really cool. And it's also just, that was, again, something that was born out of, like, we have these massive optical surveys, and somebody was like, this thing's behaving weird. It's not behaving like a supernova. It's something else. And so now having things like LSST turning on, like, we're going to, again, be like, this thing's weird. It's not behaving right. What is going on? So I'm super excited about that. Also, like, not my science, but I am so excited about Beetle Buddy, the, like, companion to Beetlejuice. I think it's so cool. I saw that you had just, like, put out a video on it recently, but I just think it's crazy that this star that we have literally been staring at since we had eyes, we just found out it has a friend. That's so crazy to me.
Yeah, I mean, a lot of the research coming out from TESS is helping define these binary stars that we didn't realize were binary stars, that when their separation is so close, and in the case of Betelgeuse's companion, like, it can't be much bigger than just the star itself. It's really tricky to make that kind of visual observation. You need a big baseline, but they are, just because they're doing such careful photometry at this point, or even they're able to examine the wake of this star passing through the outer atmosphere of Betelgeuse, they're able to make these kinds of observations. And it's amazing what they're finding.
Yeah, it's so crazy. And it also reminds me a bit of, like, Eta Carina, which is, you know, this other weird star that seems to have a companion, but also, like, may have consumed a third star in its past.
Right.
So cool. So yeah, I think everything we're discovering these days is very interesting and exciting. And I'm happy to, like, be on the come up of it all.
Yes. Yeah, absolutely. Wonderful. Well, thank you so much for taking the time to chat with me. I really appreciate it. And good luck. I look forward to the not getting a null result.
Thank you. I also look forward to that.
All right. Take care.
Thank you. You too. Bye.
I hope you enjoyed this conversation with Dr. Genevieve Schroeder. Now, we talked mostly about these kilonova events leading to potential magnetars, but Dr. Schroeder is also working on off-axis gamma ray bursts. So when you think about a gamma ray burst, you know, we see these really bright flashes because this massive star has detonated. It's produced this collimated jet, and it is pointed directly at us, like within just a few degrees. But that's very rare that you're going to have this star that happens to be so perfectly directed at us. Could there be ones that are pointed in other directions that we could recognize were gamma ray bursts and not some other flavor of kilonova or supernova or something like that? And then we could find there's a lot of these going on around us and get a sense of what is the precursor object. Like, why do you get a gamma ray burst and not just a regular supernova? So as always, I put this longer version of the interview over on Patreon. Now, it's completely for free. You don't have to pay us. You don't have to become a patron. You can just go watch it right now. I'll put a link down in the show notes. And we really feel that a place like Patreon, which doesn't put any ads in the videos, is a much better viewing experience. And so we want to reward you for getting less ads by watching it over on Patreon. Now, I'm going to give you some final thoughts, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Bear Lake Roofing, Brian Bodie, Caradwin, Chuck Hawkins, Commander Baylock, Cy Nielsen, Dark Finga, David Gilton, and David Metz, Evan Pro, Greg Feely, James Clark, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Marcel Sitz, Michael Purcell, North Space, OneStepForAnimals.org, Paul Roebuck, Brent Kaidu, Richard Williams, Sean Sargent, Stephen Fowler Munley, Team 49, Telescopes Canada, Wolfgang Klotz, and Zeldabor Galactic Defender, who support us at the Master of the Universe level, and all our patrons. All your support means the universe to us. You know, I am always super fascinated by magnetars, type 1a supernova, but the thing that I am most interested in is surveys. And I never thought, like, if you went and talked to 10-year-old Fraser who was interested in astronomy and said, one day, Fraser, you will be obsessed with surveys, databases of the night sky, I would not understand what you were talking about. What's a database? But here we are in this time where it feels like the most effective ways for us to be able to make progress in astronomy are these giant surveys. You know, I won't shut up about the Gaia Observatory, and now I'm so excited about the Vera Rubin Observatory. And then Dr. Schroeder brought up a new survey in the radio that I wasn't even aware of that now I'm going to rabbit hole into. And this is a way where you don't have to you don't have to book active time on a telescope to answer some specific question. The data have already been gathered for you, and you just have to look through them to find answers and find patterns and get a sense of what's going on out there in the universe. And you know, obviously the astronomical community is way ahead of me in this fascination with this idea and are producing all of these different kinds of surveys with more and more of them coming online all the time. And like, I hope as you've been watching more and more of my channel, my infectious enthusiasm for surveys is starting to blend onto you as well, bleed off onto you. And you're now, you know, pricking your ears, listening when you hear some new and interesting survey that's going to be coming along, that's going to give us all of this information. So all hail surveys. All right, we'll see you next time.